Welcome, I'm Simon, and in this video, I will teach you quantum hardware design. We will take a look at RF PCB or RF amplifier design, specifically RF LNA, suited for 6 gigahertz or so frequency range. So it is quite a high frequency, and um, it's just RF, very nice. So the structure of this video, it is 30 minutes, introduction to RF theory and design of PCB circuits. Uh, in this part, we will take a look how to really design your PCB circuits theoretically, following some rules and recommendations and guidelines to really have some knowledge about designing RF circuits. Um, so this is very important. In the other part of video, we'll take a look at circuit simulation, layout, and we will also talk about manufacturability, how to really export your Gerber files, and how to prepare it for manufacturing. Um, there is usage in different quantum computer types. One main computer type is spin qubit technology. The other type is superconducting technology. So there are two main types of technologies which you can use for designing your quantum computer. So very nice. So here's our quantum computer architecture. Previously, we looked at designing cryo stuff, which sits here from 10 millikelvin to 4 Kelvin. So you have your cryo stuff here. And now you can see that there is also one additional amplifier which sits at room temperature. So this is our kind of added RF amplifier just below the control electronics. So there is another RF amplifier which you need to add before control electronics. Um, so it is really nice to see. Um, now notice few similar pages from previous RFIC design video. We would require the knowledge of transistors and RFICs to really design and choose good integrated circuit to really design a proper RF amplifier PCB board. So it is very important to know something about RF circuits. So there are different types of technologies. We talked previously. There is bipolar technology, which is uh, quite old and not very often used uh, for really LNA design. There is CMOS technology, which is newer, more advanced, and more suited for RF technology and LNA stuff. Uh, this is good for a few gigahertz range, and there is hybrid technology, which is by CMOS uh, technology, which is kind of combination of both worlds and uh, most interesting parameters, and it's very popular for very high frequencies together with proper choosing of your good substrate. So there is comprehensive breakdown of different devices and different substrates. There is silicon in the first table. There is silicon bipolar technology, silicon LDMOS technology, which is more advanced than just simple MOS technology, and gallium nitride technology. So let's break it down simply. We need to look for gain, which you can see bipolar with silicon is very low. It's better with LDMOS. We can take a look at the maximum frequencies. So you can see the maximum frequencies are quite bad for silicon technologies. For gallium nitride, it is very good. It can go above 10 gigahertz. So very interesting. Uh, we also might need to take a look at the price. Uh, in this case, the most interesting are LD-MOS and gallium nitride, um, and the voltage is quite fine for both. Like broadband matching capability is very important because you can see for silicon technology it is really difficult to match it, and nobody really wants to spend time matching your circuits. So this is really where gallium nitride is very good. Um, and the gain is also very high for gallium nitride. So there is more simplified table which shows different technologies and different substrates, but also only covers maximum operating frequency. Um, and it also says whether it's in a stage of R&D or production ready or both. Uh, so silicon technology, you can see it is quite low and not that interesting in our case. There's more interesting technology, which is a gallium arsenide here in the middle, and you can see it covers frequencies um, around 20 or 60 gigahertz or so. So it is more interesting in our case to really look for the substrates and technologies in this spectrum. Very important to pick your good substrate and technology if you're designing a good RF amplifier. So this is wrap to our comprehensive breakdown devices. There is also RFIC chip preview or a decapped LNA, which only shows how the LNA looks inside. Um, you can see you have four transistors, Q1, which is here, to Q4, which is here, and you have a few inductors here, which are these kind of spirals, rectangular spiral shapes here, and you have coupling or DC block capacitors in the way which are placed, oftentimes they're placed in series for our trace. So this is very simple CMOS LNA die inside. Mm, so this is the preview. For S parameters, if we are designing good RF amplifier port, we need to really understand a few of these. So there is really the box here is really our device, and we need to understand how to plug our either signal generator or preferably VNA to measure it. So there is our input side and port S1 parameter here and S2 parameter here, and all we need to measure is S21 parameter, which is S2 is here and S1 is here, so it is gain parameter for our amplifier. Sometimes you can only measure reflections, which is S11 parameter, which is here, and this is all we need to know how to plug our VNA. So for more advanced and complex stuff, we also might take a look to impedance profiles, but this is mm, more kind of advanced stuff, and it is required for design of let's say like qubit technology itself, like chip technology. It is more kind of towards this side of design, how to really do your qubit modeling and understanding impedance profiles and parameters for your qubit modeling and chip design itself. There is also impedance matching. So here is our amplifier, and for LNA, oftentimes they're internally matched, so you won't require any input matching network. So the all you need to do is really put your amplifier and put your DC block capacitor or coupling capacitor in series, and you don't really have to input about or you don't have to really care about input matching network because it's internally matched for 50 ohms. All you need to do is mm, impedance matched trace. So the your trace is really 50 ohms impedance, and just plug your signal source or some instrument, either VNA or spectrum analyzer, and this is all you need to do for your LNA amplifier matching. There is also Smith chart. It is also important to really understand how the Smith chart works if you want to really analyze your circuit and know what impedance is at the certain frequency. So you have your frequency sweep trace here, and yeah, this is uh, kind of mm, kind of sweep uh, from one frequency to end frequency, so it's just frequency range, and at the certain point you will know your frequency and also your impedance profile. So let's say at the frequency of 5 gigahertz you have 50 ohms matched circuit. So this is really our trace. Also important to know that right side is open circuit, left side is short circuit, upwards is inductive element, and downwards is capacitive element. And this is all we need to know. There's also third order intercept point, which is sometimes um, kind of I would say important for other types of amplifiers like power amplifiers and really RFIC design. But in LNA design, we can also take a look at this. There is some input power and output power on the vertical axis, and there is some compression point um, where the amplifier really is not linear anymore and is biased and won't amplify the signal anymore. So it is also important to really understand this fundamental kind of area or knowledge or aspect of amplifiers. Uh, so for higher frequencies, we would require and need to understand the behavior and influence of different substrates. So we can break down the different substrates here. So in general, the silicon is old technology and very slow, so we can abandon it. Gallium arsenide is very popular for hemp technology. Gallium nitride is very popular for high power RF technology. So yeah, it is indium phosphide, which is for microwave frequencies, which is for very high frequencies. Typically 1 gigahertz, 100 gigahertz and above. Um, so here is our LNA chip specification. Uh, this is really a breakdown or kind of explanation of um, RFIC chip from selected Qorvo chip. So in our case, it's QPL 9058. This is our chosen RFIC chip, and I picked the datasheet and extracted the most interesting features and most interesting details and put it into presentation. So this is really here is our chip pinout, which is amplifier here, and you have RF in and RF out, and ground pin and bias pin and shutdown pin, which is controlled by some DC signal, right? And you have some most important features, which is bandwidth, which is from 500 megahertz to 6 gigahertz, and this is operational bandwidth. And then you have low noise figure, which is uh, kind of mm, noise figure at a certain frequency, right? You have mm, dBm. This is our third order intercept point, and this is the power. Here is our small signal gain value, and um, it says it's controlled by 1.8 volts logic. So here's our LNA chip layout. You can see there is some preview layout made by Corvo, and this is really some example test layout or mm, kind of evaluation board, if you will. So very simple one, very intuitive and very simply designed. Here in the top section there is our really circuit, and below there is just trace which connects two ports though with some coupling capacitors, and this is just for kind of matching your 50 ohms and for release setup of your instruments if you want to measure it. So this way you can prepare your VNAs or your test instruments. Mm, um, Now there is a very very simple layout which is just for test purposes. So this is just to evaluate the circuit. If you want something very specific and something more advanced, you will most likely need to sit down with experienced engineers and kind of design your own circuit, which is more suited for your operation and is more advanced. And like I said, this is just a very simple evaluation circuit, so you would require to really design something which specifically fits your needs. There is bill of materials for each transistor, for each component. There is component value and short description, which component you need to choose. So this is really important. Also, there is some recommended table how to choose your resistor in order to design your custom circuit. So you would most likely need to sit down and prepare your own circuit, simulate it, and see the results and just adjust it. So there is our LNA chip layout recommendation. You can really see some example test layout here, and there is a really breakdown of your PCB material and stack up parameters. So here you can really know what kind of materials and copper and how to set up your foundry and um, fabricator to really manufacture uh, proper kind of PCB for you. So here's more detailed pin description. You can see first pin is bias pin, which sets the LNA bias current for the device. Very simple one. This is DC pin. You have RF in. This pin is internally matched to 50 ohms, like I said in the previous slides. You don't need to really match it with external components. All you need to do is DC block capacitor in series in a trace. There is a shutdown pin which requires DC voltage. You can control it with MCU or any logic you wish. There is RF out pin, which is also internally matched, and you also need capacitor, and you will supply mm, the power to the chip by connecting some inductor in the trace, and this way you will really supply the LNA. So there is no supply pin for LNA. So you will supply it this way. And you also have a ground pin which needs to be connected to ground to fully ground your chip and assure proper operation. So there is LNA chip table for S parameters and noise parameters. So there is really table or set of different frequencies, and each frequency corresponds to different S parameter, and this is the same for noise parameter. So it's great to orient in this chart. Uh, so there are some LNA plots which we really need to understand. Now, the most important is gain versus frequency plot, which says um, yeah, how much gain you will have for specific and certain frequency of your chip, and this is probably the most important one. You don't really need to care that much about other charts unless you're facing some problem and really need to uh, kind of solve some issue with your chip and kind of debug it. There is also some condition for which it is measured. So the supply voltage is 5 volts and the current is 50 milliamps and it's 50 ohms match system. So this is really our CMOS LNA, and it is for oftentimes or almost always there is frequency on the x-axis and other parameter on the y-axis, unless you're really probing um, against output power or something, but this is quite unusual. Tips for manufacturers of ICs. There is Cuervo, which is for RF and microwave frequency chips. There is also Volspeed, which is for more kind of high power stuff. And there is also analog devices, which is also very good for analog and RF stuff. So now some tips regarding PCBs. The first thing is bias. Stitching and shielding. It provides protection against unwanted behaviors or some electromagnetic stuff. So this is really called shielding, which shields the trace, which shields the trace. Uh, so this is really bias, which shields. Um, yeah, this is called stitching, which is really you have big ground plane and you have a lot of bias, which are in rows and columns, and they just connect top and bottom ground plane, and there is like a little improvement for kind of behavior of your circuit, and it also prevents from unwanted behavior. So mm, it has highly positive influence on the circuit. There is HRF connectors. This is really important to really do HRF connectors, because if you connect your connectors with through Hall technology uh, to the RF circuit, it is very difficult to connect your other kind of circuits, or your I would say mm, your connectors or wires to the circuit, and it's just the handling is very difficult, but also there is stuff that kind of through whole technology has kind of negative influence over parasitics and unwanted behavior for RF and very high frequencies microwave design. So the HRF connectors are really the best way to really connect your circuit. And this is also mm, kind of SMT technology, or you can just simply connect it, I think. So edge plating is this gold frame, which kind of shields the whole circuit and provides connection to the ground, so you can connect it to some chassis, or some kind of it's a aluminum box or whatever. So this is very um, very preferable. So edge plating, very important. Also, another tip or rule is components closest to the ICs as possible. So there is really you can see the components are very close to the IC. You can see the connection to the ground is directly um, there's pad, and it directly connects to the ground plane. So very important, very short pad, a 0 ohms resistance to the ground. Very important for RF circuits. Um, Traces for RF are uncovered from the um, kind of green polish, or green cover, whatever it is, on your PCB. So this is really uncovered. and this is just copper, which is gold plated for better transmission and conductivity. Uh, so another very important rule. Um, so traces for DC are matched. Yeah, so traces in general are matched to 50 ohms, and if we use the traces for DCs, and you can see they're complementary, so it is good rule to really make them symmetric and nice and visually attractive. DC connectors, you can see the DC connectors are here. You can either choose DC connectors with SMT technology, so it won't have any hole in it, or you can use a big chunk of plane for your pad and then connect it with through hole technology. The good idea is to make them simple and with lowest resistance. So yeah, a few rules to follow, or just simply keep in mind as short traces as possible for your RF circuits, either straight line or little meanders. And if you, yeah, little meanders as possible. So this is very important. If you need to use meander, it should be either curved or chamfer traces. Um, so you really ensure uh, mm, kind of best performance for your RF circuit. Uh, it should be controlled impedance for your all your RF traces. So you should really calculate your impedance. It should be 50 ohms. Almost always should be 50 ohms. You should be really careful with your bias. Um, so yeah, either stitching or shielding for ground plane. So the shielding is really very close to the trace to kind of make sure the performance uh, is as high as possible, and the circuit is um, very high quality. Mm, so yeah, staging for ground plane. This is also very good practice. And caps should be closest to IC as possible, so you have almost zero parasitic effects. So this is very important as well. How to do impedance match PCB traces? It really depends on the width of conductor, thickness of substrate, and type of the electric, and its mm, kind of yeah, the type of your substrate. So you have FR4 and kind of ceramic substrates. So there are different materials, and they would require a different thickness of substrate, and you need to choose either strip line or coplanar waveguide. So this is like very simple breakdown how you really make your impedance match circuits. How to really choose your PCB substrate. So FR4, they are cheap and they are for low frequencies, and oftentimes they are used for digital circuits. There are like ceramic substrates which are expensive and can run reliably for 10 gigahertz, and they won't heat up and they won't do any negative behavior and won't have any negative influence over your circuits. So ceramic substrates are very highly recommended for your very high-end circuits, and you can also do combination or both. This kind of hybrid technology that for each part of kind of your PCB, you will use a different substrate, so you can kind of combine it for digital kind of part and technology. You will use FR4, and for very high frequencies and RF and microwave stuff, you will use ceramic substrates. Uh, yeah, I think this is really it, and it's simple and understandable. So there is a simulation of RF circuits. For this, you can either use built-in feature in Altium. This is really for simulation of uh, not really that important stuff to RF, but you can kind of simulate the simplest features like DC DC stuff and heating and stuff like this. For more advanced RF and microwave simulation, you would require and use AVR or Keysight with imported model of your RFIC circuit, and this is really that you would download your circuit from manufacturer website. Um, so this is really one way to do it. Uh, or yeah, this is probably the only way to do it because manufacturers oftentimes just simply provide you with the model, so you can easily use it with your desired simulation studio or microwave studio. So I would say this is the only way. Mm, uh, for the other types of kind of simulations, you might need to really export layout to some FEM simulator and really see the properties of the circuit in some FEM simulator. You can some you can really simulate more mechanical properties and more kind of properties like heat and hmm, how the waves propagate in the circuit and stuff like this. You can simulate fields and stuff like this. So this is probably the one of the kind of less important in your um, when you're starting. So this is for like very high end stuff, and hmm, yeah, this is for big corporations. Um, or the other way is to really use simple and free tools by manufacturers to really verify usability. Some manufacturers really created some very simple um, kind of tools which you can download. They're free and they are very lightweight, and you have some examples, so you can very quickly and like very simply run them. It's just prepared for you. So this is the other way, instead of using paid and very high-end studios like AVR and Keysight. So this is more for evaluation. So this is our RF amplifier workflow. You start with concept, you do some lumped elements, you just design your circuit, then you do circuit simulation, then you do layout of your RF circuit, and then you do FEM simulation if needed. If not, you can just skip this step and go straight to fabrication. And once the RF amplifier is fabricated, you can really simply measure it and see its performance once it's really fabricated and done. So yeah, the film simulation is probably required if you have really very high expensive circuits, and the circuits which require some certification and mm, well, yeah, stuff like this. So PCB design tools, you can either choose from Altium, which is paid and a very strong tool, or KiCad, which is very simple and free. So it's your choice. For circuit simulation tools, you can either choose Keysight, which is paid and very strong. You have a lot of different features, or Comparator, which is AVR, which is paid and also very good. So it's just up to you which one you choose. For FEM simulation tools, you have a lot to choose from. You have either ANSYS, which is paid and very strong, Elmer, which is free and lightweight, and Palace, which is cloud-based and also very good. Where to manufacture your circuits, there are many options, and it really depends on your needs and quantity, and also your geographic location and preferences. So also level of professionality, because some PCB manufacturers kind of offer more advanced kind of nodes or a more advanced approach to really designing your circuits, and for you it might be really beneficial to really prototype and manufacture your circuits locally. Really manufacturing in PCB in China can be cheap, quick, and for very high quantities. But also manufacturing locally can be kind of very um, very reliable, and you can directly talk to the staff or personnel there, and it can be you might benefit from different kind of approach, or kind of you might be able to just uh, go and see the process and see your PCBs being manufactured. So it might offer also some benefits for you. So it's really up to you. What do you need, and what do you want from your manufacturer? So there are some tasks or paper or channels or books to follow. So for some resources, I picked Altium Academy, which is very professional, made by uh, Altium, the corporation which really created the Altium software. So there are people who really work for Altium and know their design stuff. So this is uh, really the first place to look, and then you can search for separate influencers, like for example Zach Peterson, Robert Verhonek, or Phil Salmoni. So you can really choose what you really need. So there are some handbooks and some materials to really design and to really follow the design for manufacturability. So the first place is really Altium Design for Manufacturing Handbook. This is really the first place to look at, and the first thing. The other is Designer Handbook for DFM, and the other is about controlled impedance, which is from Sierra Circuits. So also a very nice place mm, to look for your design knowledge. So if you really like my stuff and you have something to say, or just interested in talking to me, you can contact me either on LinkedIn or Gmail. So here is our open circuit in Altium. This is the place where we actually design our amplifier. You can use it for various different RF circuits, even analog ones and digital ones. It's very simple, and it can be used for very different kinds and types of PCB designs. In our case, we will design RF LNA for 6 gigahertz. And so this is our preview of our RF LNA PCB. And let's very simply break down the circuit in 3D view. So this is really a preview for 3D view. We can break it down. So here are RF connectors. They're edge mounted. This is very beneficial for RF performance. There is our capacitor, which is in the way. There is a bias circuitry here, and there is supply pins and supply kind of components, passive components. So this is really our circuit. Here is our RFIC. So this is very simple breakdown of our circuit. Now let's get moving to really designing something. First, we need to create new schematic, and then we will create new PCB file. So we click on this. I already created this. So here is our schematic of our RFIC LNA amplifier tuned for 6 gigahertz. There are some pins here, so it's just simple connector here. We need to add some passive components like capacitors and resistors, and select the proper value. Then we need to assign, this is called namings for the traces. So if we click the trace, you can see the net name. It's called net name. We can do this simply by creating net label after placing wire. So here is our really net name. We need to assign ground planes, which we do by clicking this symbol. And once we have all this done, we need to add components such as connectors, and we can simply finalize our circuit by really completing all the connections. Once the connections are completed, we need to assign impedance. For controlled impedance, we need to really create this symbol, add this symbol, and we can do this by simply selecting parameter set and choosing RF in design. Let me once we switch to the sheet, then we click to design and layer stack manager. So this is where all the impedance are defined, and here is really our our PCB stack up. We can click add, and or we can click impedance. We can click add, and we will add 50 ohm impedance here. It's very simply defined here. So once we have schematic and layout, we can simply push the files to the production. So in order to do this, we can really click fabrication outputs and create NC drill files. And once the NC drill files are ready, we can create Gerber files. And this is really just for PCB. So this is our PCB description files. And then we need to create assembly outputs. And in order to do this, we click assembly outputs and generate pick and place files. So now once we have all the files ready, we can really push our kind of PCB to production, we can just simply really break down the layout itself. So we can see we have some keep out layer, which is just lines. We can do this by selecting the line and creating the line in proper layer, which is here. This is keep out layer, so we will just make the board or kind of, let's say, just keep out frame for our PCB. And once this is really done, we can go to design, board shape, and define board shape from selected objects. It will create the board shape for us, and once we have board shape, we can really drag our components into the proper places. Once we have our components in proper places, we just click route and we will route the components properly. And once this is really done, we go to design, or tools, tools, polygon purse, polygon manager. We click on polygon manager, and here we just create new polygon from board outline, and it will create a new polygon for us. And we will select ground plane, and this will create the polygon ground plane for us. So this is the red thing here. So this is the red thing here. So this is our ground plane. Then we can go to stitching and shielding, add stitching to the net. This will create the stitching pattern, and then we can add shielding to the net, which will create the shielding pattern around the traces, which we can see here. This is the shielding pattern here, really. And once we have all this done, we can add the holes, and holes can be added using path. We just create the path, and this is really our hole. We can change its properties here in the properties panel. We can change the hole diameter, which is just simply changing this value, hole size, and it will create the simple hole. We can also choose to do little frame from copper around the hole, which is great for mounting and connection to the ground plane. So this is really recommended. We can also just simply create the very thin trace around the board, which will create a kind of grounding little trace, so we can simply connect our enclosure or aluminium box in order to close this wonderful RF amplifier PCB. So this is really it regarding RF LNA PCB design. Oh, and that's a wrap. One more thing, if you have something to say, please feel free to contact me either on Gmail or LinkedIn. Thank you.